This is the part which we will use for this demonstration. It's a simple molded plastic part. It belongs to a garden appliance, and the objective is to create a copy of it. First, we will scan the object. For that, we put it on a dedicated table, which includes targets, which are these white dots. These targets are used by the scanner to define its position in space throughout the movement. There are some targets also on the object, because it's big, and the scanner wouldn't be able to find its position in space if he had no target on the object. The points are scanned and sent to dedicated software which is provided with the scanner, and which allows us to export the result in different formats. One of them is the OBJ format. What's interesting within the OBJ format is that it includes the texture of the object. This format can be imported into 3DEXPERIENCE. You will recover the texture because the scanner has read the texture, has captured the texture. But this object cannot be used for the recreation of exact geometry. For the recreation of exact geometry, I need to go to a design environment, to a modeling environment. So create a 3D part, for example, and I will use the digitized shape preparation application of Catia to import the same scan but in STL format. The STL is just a tessellation. That means it's a cloud of points in which points are connected 3 by 3 by triangular facets. Of course, it overlaps exactly the OBJ that we have imported before, but this one is an object which is usable for design. So if I open this part alone, I go to the digitized shape to surface application of Catia. This application includes a wizard which will allow me to recreate an exact geometry from that tessellation. For that, I will define a design space, which could be an existing solid or, like in this case, just any containment box that includes the mesh. And I will split that box to make it to fit it to the object. So first I will split it by the horizontal plane, and you see that now the part is limited to the right plane. So that's easy. Second split operation will be by the side of the object. So in digitized shape to surface application, I have a tool to recognize a plane here, an exact plane. So it will fit the best possible plane through the points of that face of the mesh. Okay. And then in the wizard, I have a split command, and I will define the plane as a splitting element. I just have to be careful that I will keep the right side of the object. So for that I have to find and give the right direction to the arrow indicated which side is kept. And now you see that the design space has been cut by the side plane of the object. So that's very easy to do, and we will go on with the same method for other planes. So now we will recognize the top plane here. Okay, so we just have to select a point on the top plane, and the corresponding plane will be automatically recognized. Okay, and this plane, once it's created, can be used as a cutting element to cut the design space. So the concept is very easy. You just have, using the reverse engineering functions of Catia to recognize the main elements of the shape to recreate, and the wizard will let you create the part step by step, starting from a design space. For that side, I cannot split by a single plane. I have to create the two planes. These two planes, and then I have to assemble them in order to create a cutting element. That's not complicated. I will just use the regular trim function of Catia to limit the planes to each other, so that I have now a simple surface, and this simple surface can be used to split the design space. Okay, so there are some more splits to do. So there's a front plane and the back plane. Okay, that's not complicated. Let's skip these steps. Now there is on the top of the object a surface which is not a plane. This is a freeform surface. So I will have to approximate it with a different tool. I will approximate it with a power fit surface, and for that I need to select which planes I want to consider for the creation of the freeform surface. Okay, so I don't need a perfect selection of the points. It's no problem if there are some facets missing. I will give an accuracy, and if I apply, I see that I create a large surface, smooth, large surface that covers the selected points, but which is extended outside the area of the points. If I check the segmentation, I see that I have created a B-spline. It's not so bad, it's smooth. If I try to reduce the tolerance, which means increase the accuracy from 1 to 0.5, you see that the surface starts to be a little bit wavy. It means that I probably reached the limit value that I can request for the tolerance. This is no surprise, because the type of scanner which I have been using is usually working within the 0.5 accuracy. Now this B-spline surface is used to split the object, as we did with the planes earlier. Now if you redisplay the whole object, you redisplay the design space, you see that your design space has been limited and split and cut and sculpted in order to fit the main surfaces of the mesh. Now for the creation of the part, of the final object, what you have to do is no longer reverse engineering. You have to go to classic mechanical design. So for that, we will go to part design and complete the object with part design features. You can notice that even though you go to part design, the wizard window, the wizard box, remains active, so that you can still use it, for example, to change the transparency of the object, or to hide and show the mesh, hide and show the object itself. Or you could even go further and add new cutting elements. But now, okay, first operation, classic mechanical design operation, create an edge fillet along that edge of the object. Either you know the value of the fillet, or you define it visually by trying to fit to the mesh. Okay, that's classic, really classic mechanical design. Second operation, so create this bigger mesh here. this case the radius, so you can try with the radius 25, seems to be a little bit too big, so you reduce it until you think it's the right value. Anyway, this fillet will be editable afterwards. It's a regular part design feature. So 22 seems to be a correct value. Here, let's assume that it's the same value. So create a fillet radius 22. And also here, in fact, so could have done it at the same time, but let's do it now. It's okay. Very good. Okay, so now all fillets have been created. And the radius can still be changed if necessary. There is another important feature of part design that has to be used now, which is the shell, because this part is a thin part. I use the regular shell command of part design. I select the faces which have to be removed. If I confirm, I have created the shell. And now it is very close to my surface, except that I forgot to choose the thickness. But it's no problem. You can see in the tree that all features are available, accessible, and can be edited. So I just have to edit the shell feature and turn the thickness to its exact value, which is 3 millimeters. And everything is updated, of course. That's no surprise for users of Catia. If I compare, if I redisplay the mesh, I see that it's okay. I'm almost finished. What is now missing is the detailed shapes, or are the detailed shapes which are on the top face of the object. So these shapes have dimensions probably, and they are also probably available from the other parts of the product, the parts on which this one is supposed to be assembled, to which this one is supposed to be assembled. So it's not really reverse engineering, it's also classic mechanical design or context design. Okay, just to give an idea, if the dimensions are known, it's possible to create a sketch, and create a pad, and add the pad to the current object. So that's also classic mechanical design. It's not reverse engineering. These shapes are known by their dimensions normally. Okay, so once all these details have been added, this is the object which we get. And what we need now is to create a mesh, a tessellation, that will be sent to the printer. That's easy, that the tessellation is done within a given accuracy. If we zoom, you can see that it's no longer a smooth surface, it's made of surface which is made of facets. And this object can be sent to the printer. So actually the printer that I'm using is an office printer. It's a small one, so I'm not able to print the part scale 1. So this is in fact a print of scale half scale part, scale 0.5. But if I had a bigger printer, I would be able to create a scale 1 copy of the object. So after 2 hours, more or less 2 hours printing, I have a new part with some supports have been automatically removed, but there are some supports to remove inside the holes here, and this is a copy of the original object. Now I may want to control the shape of this object which I have printed. So I will go back to my scanning bench, use the scanner, and measure points on the printed object using the same acquisition software. I will export the points from the acquisition software as an STL in order to import them back to Catia, and I will compare this new scan to the object which I have recreated before. So I don't want to use all the points. I need the main surfaces only of the object. I don't want the table, the points which are on the table. Okay, if I confirm, I will keep these points for the control operation. I have previously extracted the skin of the object which I have designed earlier. So of course the scan points are not in the same position as the object, as the design object, so I have some alignment to do. This is very easy because I will be able to use these 3 planes to make an alignment by constraints onto the planes of the designed object. I will define the first constraint, which is that this plane should arrive on this plane. A second constraint, that this plane should be sent to this plane. And the third one, this plane must be sent to this plane. If I apply a geometric transformation has been applied to the mesh so that it is now in the same position as the designed object, as the reference object. And now I will be able to use the deviation analysis tool of Catia in order to measure the distance between these 2 objects. The reference object is the exact surface. The object to measure is the scan. I have a number of parameters. Okay, if I click apply, I have a color map. The distances are given by a color map, which is hidden by these boxes, but that I will bring back. And I can see that the color map tells me that 100% of the points are within a tolerance of plus or minus 1 millimeter, which is not so bad